We started work, power, and energy last week. We talked about different kinds of energy. We looked at formulas for kinetic energy. We looked at formulas for potential energy. For gravity, we did potential energy for a spring. We talked about that guy there. Potential energy spring is half kx squared. We talked about what it means to do work. Work being a force times a distance. If you don't actually, you can apply a force all you want. If nothing actually moves, you haven't done any work. And we figured out a way to find overall work done or net work. Today, this is just this page. We're going to look at another way to define work, and then we're going to look at analyzing another form of graph to find the amount of work done. So let's go. So we define work as a force times a distance. We looked at the units for everything, and we saw that every time the units showed up the exact same way, whether it's kinetic energy, potential energy, spring potential, or potential gravitational, spring potential energy, work, all of them have units that convert the same way into joules. And so because they all work the same way, then work must just be a form of energy. And so we can use that idea to redefine how we look at work. Work can be defined then as a change in energy. To change an object's energy, another way to interpret that is to change an object's energy, you must do work to it. And so what that looks like is this. If work is equal to a change in energy, we're going to get work is equal to delta E. Well, a change in energy is just energy final minus energy initial. And so we can actually do some rejigging to this expression here, which will be not tomorrow's lesson, but the lesson, tomorrow's Storm the Wall. But I have you guys last blocked. Storm the Wall is an extended lunch. 11:30 till 1:15. So just under 2 hours.
So is that A block?
No, it goes C, D, A, crazy long lunch, and then I see you for an hour and 5 minutes.
Are they all
Sorry?
Are all the blocks
Presumably. I don't actually... Lunch is from 11:30 to 1:15. So from 8:10 to 11:30, you have 3 blocks. So presumably they're all an hour and 5 minutes. It's just like it's the same length as a pep rally, except it's after lunch instead of before lunch. Okay, so if we rejig this, I was gonna get you guys to do some running in class tomorrow too. We'll see how it goes. Yeah, you're gonna do a lab. You're gonna find out what your power is, how much horsepower. But this is one of those in-class only labs. It's short. This one's way shorter. So anyway, if we rejig this, if I add energy initial to both sides of the equation, it's going to move from this side of the equation, and it's going to show up over here. And so what you're going to get is that whatever initial energy you have, you might not have any. If you're not moving and you're at ground level, you have no kinetic, you have no potential. If you're running already, you have kinetic energy to start. If you put in a little bit of work, these are both measured in joules. If you are moving already and you add some more energy, your final energy is going to be larger than it was to start. And so this guy right here is likely going to be Wednesday's lesson on something called the work energy theorem, which is a neat little, wildly useful little equation. But for today, we'll just look at it in relatively simple terms. Rushan, good morning. Here's a way you can apply this. So a 5 kilogram object is accelerated from 2 meters per second to 5 meters per second. We want to find the work done required to make that happen. And so what we're going to do is we're going to start with this. Actually, it doesn't really matter which expression we start with here. The easiest one to start with is this guy here. Because we're just looking for work and we're given two different states of the object. So what we want to do to find the amount of work, we want to look at how much energy the thing had at the end minus how much energy it started with. And the work energy theorem, or the idea that work is defined as a change in energy, it doesn't actually care or specify what kind of energy changed. If you want to change any kind of energy, you have to do work. If you want to change spring potential energy, you have to compress or expand the spring. It moves, you do work. In this question here, we want to accelerate an object from 2 meters per second to 5 meters per second. So what kind of energy are we changing? What kind of energy changes if you're speeding up an object? But what kind of energy is changing? You are accelerating. Sorry? Kinetic energy. The object is moving, that's kinetic energy. So, to find out how much work is done, we have to look at the kinetic energy at the end, and we want to take away the kinetic energy at the beginning. KE final minus KE initial. Well, we know kinetic energy is, if you have forgotten or you weren't here, but you would have looked at it last year, it's also on your formula sheet right here. Kinetic energy, EK, equals 1/2 mv squared. The mass isn't changing, so this is just going to be 1/2 mv final squared, don't forget to square it, minus 1/2 mv initial squared, and we can plug it all these values in. It's going to be 1/2 a mass of 5. At the end, the final velocity was 5 meters per second squared minus 1/2, oops, that should be a 5, not an m, times 2 squared. So you can round that through your calculator. Well, actually, we don't need to round that through our calculator. 2 squared is 4 times 5 is 20, and half of 20 is 10. That's going to be 25. 25 times 5 is 125. And then half of 125 is 62.5. So we're going to have the work is going to be equal to 62.5 joules minus 10 joules, means to change the velocity of this object from 2 meters per second to 5 meters per second, you had to do 52.5 joules worth of work. That's it. Questions, comments, concerns about what we've done? Some of you are still writing, okay? I mean, the next example is the same, it's just a different kind of energy. A 10 kilogram box is lifted 5 meters straight up. What was the work done? Well, what kind of energy is changing here? Work is going to be equal to a change in energy. If you're lifting a box straight up 5 meters, what kind of work is, or what kind of energy is being changed? Potential energy. So this is going to equal a change in potential energy. I'm going to write this one out a little bit differently than we did before, just to show you another way to interpret this change. So this is going to be equal to a change in mgh, because that's what potential gravitational energy is. We'll call this PEG. What's changing? Is m changing? Kai says the height is changing. Yes, the height is changing. So I can rewrite this. I can say, okay, well, this is going to be equal to m times g times the change in height. Do we know what the initial height is? Doesn't matter. Why doesn't it matter, Kai? It doesn't, because they gave it. It doesn't matter where it started. We're told it's lifted 5 meters. It could start at the floor and go up 5 meters. It can start at 2 meters and go up to 7 meters. It doesn't actually matter where the thing started. The amount of joules you need stays the same. You know it's been lifted 5 meters. So this guy right here is how you can, wow, Kai, that was shots fired. This lifted 5 meters means your change in height is equal to positive 5. The final height is bigger than the initial height. It's gone up 5 meters. If this was dropped 5 meters, this result would be negative. Good. Because the final height would be lower than the initial height. So we can find the work this way. We could say, okay, well, work is just going to be equal to the mass times the gravity times the change in height. And the mass is 10, gravity is 9.8, and the change in the height is 5. So 10 times 9.8 is going to be 98. 98 times 5 is going to be 490 joules. You can, again, if you read the question carefully, you can interpret your way through some work. Or, I mean, we could have just as easily done it the long way here and said initial height 0, final height's 5. It doesn't actually matter what the two heights are as long as the change in between them is 5 meters. So this is relatively straightforward as long as you have relatively straightforward scenarios. In this question, the force was constant the entire time. It doesn't get harder to lift something the higher it gets, for example. But when you have a scenario where the force changes as you act, like a spring, for example, as you extend a spring, the more you extend it, the harder it gets to continue extending it. Or if you wanted to compress a spring, the more you compress it, the harder it gets to compress. When we analyze those kinds of scenarios where the forces are variable or the forces are changing, we actually have to do it graphically. So this is an example where you have a changing force as distance changes. This is, for example, or useful for changing forces, i.e. springs. Because if you recall, the force on a spring is equal to K, the spring constant, times its extension or compression. And so as this changes, this is going to grow. And so to analyze it, we've really got to do it graphically. If you recall as well, work is going to be equal to a force times a distance. So if I'm multiplying forces and distances together, what am I finding on this graph? If I'm multiplying a force by a distance, what am I finding? Forces times distances are areas. Thank you. Work is the area under a force distance graph. So let's figure out the work done. Well, the question out here now asks, what is the work done in moving an object from 2 meters to 6 meters given this information? Okay, well, the 2 meter mark is right here. The 6 meter mark is right here. And so what we're asked to find is, if I want to find the work done in moving that object, what I need to do is I need to find this space. So that's kind of an awkward looking space. We've done this before. You should have seen this. Well, you've seen this in a few places. Math classes, we did this earlier this year. We want to break that thing up into two shapes. if I draw a horizontal line right across here, I'm going to get a rectangle there, and I'm going to get a triangle here. And I need to know, or I need to be able to estimate what these values are right here. Because if you look really closely, 6 meters and 2 meters don't nicely intersect the graph. If you were to ballpark what this dotted line was, or this line down here, what that value is, what would you say it is? Look at the scale on the graph. What is that value? 1.4 is reasonable. Sure. 1.4-ish. What's this guy up here? 2 point. Could be. 2.7, sure. This, if you look what's happening here, every one of these lines represents a half, right? So that's going to be a half. That's 1. That's going to be 1.5, which is why Emma said 1.4. That's going to be 2, 2.5. And halfway between 2.5 and 3 would be 2.75. And we're below halfway. So saying that this is 2.7 is totally reasonable. It's definitely not more than halfway up the little square. So you can't say it's anything more than 2.7, because halfway would be 2.75, and beyond that would be 2.8, 2.9, whatever. So if I want to find the object, the work done moving that object graphically, we're going to look at these two areas. We want the area is going to equal the area of the triangle plus the area of the rectangle. The area of the triangle is 1/2 base times height, plus the area of the rectangle, which is just going to be base times height, or length times width, or whatever you want to, whatever language you want to use. So for the triangle, the length of the base is going to be the same. It's 4 meters. What's the height of the triangle? Well, the triangle starts right here at 1.4 and it goes up to here at 2.7, which is, you bet. The difference between these two is going to give you the height. If I remember back to that first unit, a whole bunch of you just told me the height of the triangle is 2.7. You have to go from where the triangle ends to where the triangle started. Subtract those two values. So this height difference is 1.3 meters, or sorry, 1.3 newtons, plus 4 times the height of the rectangle is just 1.4. Do the math, add them up. What do we get? 1/2 times 4 times 1.3 plus 4 times 1.4. I get 8.2 joules. Find the shapes, add them up. Likewise, if we wanted to find the work done in moving the object from 4 meters to 10 meters, the procedure is the same. I mean, it's a little bit easier because if you look at 4 meters and 10 meters, 4 meters is there, 10 meters is the end. That's a nice little cut. You're on the grid. That's a lot easier to do. I'm going to leave you to play with that. So this is all we're going to do today. Tomorrow we'll start taking a look at power, and we're going to have you guys calculating how powerful you are. And we're going to convert that over into horsepower, how many horsepower you possess. And you'll see how ridiculous horsepower is, because I've had some students with ridiculous horsepowers. So your homework is going to be this question down here. Flip the page to this page, the work, power, and energy section. I want you guys to look at 1 through 10, 14 through the 18. You're ignoring this. 11, 12, and 13 we'll come back to tomorrow. So those two chunks, some of them are really easy. And then I want you to take a look at this elastic potential energy page as well. Yes, but I'm giving you basically an hour to do it. And lots of these are really simple calculations. And that's it. So take a look at these things. I'll help where needed. Let me know what I can do. Happy Monday. Welcome back. Get going. Good, man. How are you? Let's start.